I am Ajit Khaparde. I lead the DPDK effort at Broadcom. For today, I'm going to go over some aspects of RAS and how it can help in the deployments to become reliable. So we'll go over some basics of RAS, like what's the why and how. Let's start with what is RAS. In short, it stands for reliability, availability, and serviceability. So let's dig a little deeper. Modern computers are a set of complex modular components. We all know that they interact with each other. Making them like available reliably is the key to any deployment. Now, with these complex machines, they are prone to errors and failures, and recovering gracefully from such failures is what RAS is all about, especially when the solution that is deployed is on hundreds of thousands or more systems. So, why is this important? We know rebooting a system in case of a failure, it can actually take a long time. Reloading and restarting applications can take precious time as well. So if there is an error condition, if we can detect it and recover without having to reboot, or doing that in the smallest possible downtime, is what a RAS-aware deployment would actually allow us to provide. Then how do we do it? So RAS, it relies on continuous health check, monitoring, and then if there is an error, triggering a recovery. So for example, if a hardware it encounters an error, the firmware can work with the hardware and then the device driver to once the error is detected to recover from this failure. Each component involved can help gather information on why the failure happened, and it can help root cause and some postmortem analysis. If necessary, the application can also be updated with this failure information. So at a high level, you can see the steps involved in the recovery in case of a error, once an error is detected, and then the recovery process itself. So if you look at it, the key aspect here is to detect an error. And once the error is detected, the solution can be either a simple mechanism or a complex state machine, but the implementation of this whole recovery, detection and recovery is vendor specific. And then at a higher level, the hardware, the firmware, and the different components of the system, they need to interact with each other once an error is detected, and then the counterpart should work on what they are supposed to do. Like they need to acknowledge that they have detected the error and they are going to participate in the recovery process itself. One point to note here is that we may not be able to recover from all the errors, but that doesn't mean we should not attempt it if an error is detected. So once an error is detected, the hardware, the firmware, and software, they acknowledge this, and then they need to act on perform their roles. So especially like if the driver actually ends up identifying that there is an error, it actually needs to suspend any activity. Like that can include the control plane activity and the data plane activity, and this is to prevent any further damage or interference in the recovery process or any other catastrophic failures. Once an error is detected and once the activity is suspended, the poll mode driver can in fact even update the application that the recovery process is in progress. And once the recovery is successfully done, the driver can reinitialize its resources, recreate TX and RX range, reset the indices, and such. Once the various components involved during the recovery, they can gather information, as I said, about the various logs, the register dump, and whatnot for postmortem analysis. The PMD can update the application whether the recovery process was successful or failure. We have the DPDK dev library already provides flags to indicate this status. So once we know that we have gone over what exactly happens, or at a high level, what steps are needed for recovery, let's see what is the role of an application. So the first or easiest way is the passive mode, in which the application is typically agnostic. It's just not aware of the fun and fanfare that the port mode driver and the other underlying components actually went through during the error detection and recovery. But once the driver detects this, it can trap any control plane or data plane activity. It can, if necessary, update the TX and RX handlers with dummy functions so that there are there's no further activity. Once the recovery is complete, the application the driver will update its burst handlers to resume traffic, but the flow rules and shared objects, they may be lost, because since the application is just not aware of this, and the driver may have no way to replay this information. And in case of failure, the application may issue a cleanup because of some inactivity or admin intervention, but it may not know necessarily that it was because the recovery had failed. Coming to the active mode, this is where, like as the name indicates, the application is aware that that the recovery was in progress, which means it can actually be in control. The application can suspend any control plane activity or data plane activity once it gets the notification from the underlying pole mode driver. Once the recovery process is complete, again, it is going to get it would get a notification that the process was successfully completed, and it can replay the flow rules. It can recreate the shared objects and any other things which it deems necessary. In case of a failure, it knows that the failure is because the recovery was not successful, and it can initiate cleanup with that knowledge. And it's sort of like depending on some inactivity or some other error happening, or maybe admin intervention. So overall, if we like just roll back, rewind, and see, we know that passive mode works, but and this is based on experience. Application aware approach is more suitable or desirable for a good RAS deployment. So that's all I have for today.